So our final speaker for today is going to be Mina. So welcome, Mina. Mina's at the University of California, Irvine, and she's going to be talking about teaching Bayesian statistics for undergraduates. So Mina, the floor is yours.
Thank you, Eleanor. So I should first confess that I've given this talk numerous times, but this time I'm quite nervous because it's my first talk to a UK-based audience. Thank you for having me here. My name is Mina Dogucu, and I'm assistant professor of teaching in the Department of Statistics at University of California, Irvine. One thing I should mention is the Department of Statistics is actually in a computing school rather than School of Sciences. That's probably unusual for statistics department, and you will see soon why that is important for this Bayesian course. And for those of you on Twitter, maybe you might have heard this already. I'm actually on my way to joining University of College London Department of Statistical Science in the summer. So hopefully I will see some of you in person soon. So I'll be talking about my course Stats 115, Introduction to Bayesian Data Analysis. I have shared the slides link, and everything I will be sharing is also linked through the slides, so you can feel free to access everything in this talk. So this is usually a senior level course, and I will soon talk about the prerequisites and the background. But before I talk about this course, I wanted to talk really briefly about a preference we have with Monica Hu. It's actually, I thought it was very appropriate for this talk because the title of the preprint is The Current State of Undergraduate Bayesian Education and Recommendations for the Future. In short, I can say that the future is Bayesian or more Bayesian than it is currently. So in this preprint, what we did is actually look at the state of Bayesian courses in the United States. And we've surveyed 100 highly ranked institutions, universities, and 50 liberal arts colleges. And we've seen like what majors are Bayesian courses part of, what prerequisites they have, and so forth. So something that was very interesting for us was actually, of course, like it's not surprising that Bayesian courses are mostly part of statistical sciences, mathematical sciences, or computer sciences majors, or data sciences. But we've also identified actually university programs that actually have Bayesian courses as part of their public policy majors, philosophy major, even physics major, and so on. So it's actually good. It was good for us to see that Bayesian courses are part of other programs as well. And we've also looked at whether these courses are as electives or required in programs. So of the 100 top ranked universities, we've identified 4 programs that require a Bayesian course. So this gives you an idea that even though Bayesian courses do happen in the United States, at least they're not usually required courses. And I should also note that one of those 4 courses is the course I teach. So the Bayesian course I teach is a major requirement, but we do not have a statistics major. It's actually part of our data science major. So it's very hard for me to talk about the course I'm teaching without talking about the textbook that I co-authored. So the textbook and the course are pretty aligned. So there's the textbook, it's open access, you can feel free to look at it. And there's also an accompanying R package that helps supports learning in the classroom. And I should also acknowledge my co-authors, Alicia and Miles, who are, in my opinion, terrific stats educators. Last but not least, one acknowledgement I would like to say about this project is this project was not funded by National Science Foundation, but currently I do have funding from National Science Foundation, and it is helping me support things like giving this talk. So I feel obliged to thank National Science Foundation. And also the good part of it is because our efforts are to expand the Bayesian education to other institutions, it will also help us adopt this course at a collaborative institution, California State University, Fullerton. So just to give an overview of the course or the book, so it's split into 4 units. We first start with Bayesian foundation. So we start with the Bayes rules, simple models like the beta binomial model. And we talk about how the posterior analysis works, how it's a balance between the prior and the likelihood. Then we move on to other conjugate models like the Poisson, gamma Poisson and normal model. And once students are able to drive the posterior, we then move on to posterior simulation analysis. Even though in unit 1, we actually do posterior derivation, actually, even from the beginning, students start simulation. So it's a very computing-based approach to Bayesian analysis. We then move on to certain algorithms like the grid approximation and the Metropolis-Hastings algorithm. Then once students are able to estimate the posterior via simulation, we move on to using the posterior for things like hypothesis testing, credible intervals, and so on, as well as posterior prediction. And in the third part of the course or the book, we move on to regression modeling. So the book is obviously more extensive than the course itself. And the reason for that is I actually teach in a quarter system, which means I have 10 weeks of lectures. So I don't necessarily make it to all these models, but at the same time, students, for instance, I cover normal regression and then logistic regression, but students are able to pick up naive-based classification, for instance, themselves for projects. And then the last part is hierarchical models. So again, the book is more comprehensive than the course itself. I do cover in the course the normal hierarchical models without predictors and with predictors, but I do not make it to the non-normal hierarchical regression. To give an idea of the background of students taking the course, so the prerequisite of the course is Stats 120C. That means that our student, the prerequisite is a year-long sequence of probability and stats. But it also has a recommendation, Stats 110. That's our methods course, the first methods course. Since this is a requirement for the data science major, this is actually the basic requirements. What happens in reality is actually students have taken a lot more stats courses, and this course they end up taking in their senior year. It just works for their schedule that way. So by the time they get to the Bayesian course, they have actually taken a lot more computing courses, and they have taken a lot more stats courses than this. So they usually have very good proficiency in art when they come to the course. It's also our elective course for the statistics minor. So sometimes we would have students who are like psychology majors or economics majors who are minoring in statistics who would be taking this course. So now I will try to give examples from each unit or different sections of the course. So of course, we start with students with the basic idea of Bayesian statistics. For instance, in this example, we have a person who goes to taste food at an Italian restaurant, and they read online that this is a 5-star restaurant. And then they taste some noodles there and they don't necessarily like it, and they update the information to the 3-star restaurant. And they go ahead and taste more, and this time they get actually a very tasty Alfredo, and then they update their rating to a 4-star restaurant. So we try to give this very early on to students, updating information and the way Bayesians approach data analysis. And once they do that, then once we get that basic idea without any numbers or notation, we then move on to some modeling examples. So I'll give an example from a beta binomial model, since it's one of the simplest models. So the data is actually about Bechdel test. For those of you who are not familiar with the Bechdel test, in 1985, there was a comic by Alison Bechdel. She had 2 characters talking to each other, and one of the characters says that she only goes to the movies if the movie has at least 2 women in it. These 2 women talk to each other, and they talk something about something besides a man. So this, even though this is it's a binary question actually, whether the movie passes a Bechdel test or not. So in this case, students are trying to estimate pi, which is a random value between 0 and 1, and they are trying to find the unknown proportion of movies that pass the Bechdel test. So we try to build intuition in the classroom. For instance, we have 3 plots of prior ideas about pi. You might see that on the left, we have a very flat prior, and on the right, we have a highly informative prior. So what the students have to do to test their intuition and to familiarize themselves with the beta distribution, beta prior, is we give them 3 characters. One is feminist, who thinks that women are not represented enough in movies. And the other one is clueless, they're not unsure what that proportion could be. And then there's an optimist that backs out as a low representation. Actually, women are presented more in movies. So we try to have them match these. But this is just one example of what we try to achieve in the course and in the book a lot, is trying to get to students' intuition and always asking them quiz questions. But these are not graded quiz questions, but try to see what their prior ideas are. It's very Bayesian in itself. So we also support this intuition building with a lot of computing. So the Bayesrules package, for instance, to get to tuning their priors for beta prior, there are some simple functions, for instance, plot underscore beta, and students can give the parameters for the beta prior to visualize this. So they can keep trying on different parameters, arguments of the function to actually see what distribution matches their prior understanding of movies that pass the Bechdel test. And through doing this, trying different arguments, they actually get to build a bigger picture of the beta prior. How does it look like when alpha is less than beta? How does it look like when alpha and beta are equal to each other? How does it look like when beta and alpha are different? Beta is greater than alpha. So the functions, you might have realized that they're extremely simple. It's not necessarily, and they don't necessarily even have to be done in R. It could have been a Shiny app or something. But the idea here is to get students to try different parameters to help them build their understanding of the beta prior. But these simple functions can also extend to actually having them understand more foundational Bayesian ideas. So I've just showed you plotting beta, but there are also functions like plot beta binomial, and that helps actually have them try different priors, different data, so they can see the likelihood function change, and they can also see how the posterior changes. So in this picture, for instance, each row shows a different prior distribution, and then each column shows a different sample size, different data. So by actually trying these, students should be arriving at the conclusion that when there is a highly informative prior, the posterior is much closer to the prior, it's more highly influenced by the prior. And for the likelihood, it's highly influenced by the likelihood when the sample size is a lot larger. So as the sample size gets larger, even though the maximum likelihood estimates of these data are the same, the posterior will be more influenced. So once again, it's a simple R function, but it is giving a lot more than the function itself, conceptually. And I will also share another example from the posterior approximation units. And the idea here is to talk a little bit about stats and computing at the same time. So in this example, students are actually writing from scratch Metropolis Hastings algorithm themselves. So certain things to pay attention to here, in case anybody is unfamiliar, Metropolis Hastings is not that important for now. But what I would like you to pay attention to is students are actually approximating a parameter. But in order for students to be able to write this approximation algorithm, what they have to know is first and foremost understand the statistics behind it. So for instance, here we have d norm times d norm. So they actually should be understanding posterior as a proportional to prior times likelihood, and how these priors and likelihoods are taking part in this approximation process. So that's number one. But there's also another aspect, and also there are different parts, of course, of the algorithm. Similarly, like students need to be able to familiar with the statistical concept in order to be able to write this code. But also there is also a lot of computing that goes in here. For instance, like students should be able to write functions. They should be able to write sampling simulations and so on. So this is very important, I think, in my opinion, in a Bayesian course, to have that balance of statistics and computing at the same time. And once they write that function, they write that into another function. Similarly, there's computing going on here as well. But what happens once they can actually write those functions is they can get to a posterior approximation themselves, because they will have at each iteration an approximation. So once they have that posterior, then they're able to do posterior analysis. They can actually look at the density plot. They can actually look at trace plots and comment on the state of, for instance, the iterations. And similarly, once they have these iterations, they can do further posterior analysis to like building credible intervals or hypothesis testing as well. But the good part of it is they have done all of this themselves. But once they are actually able to write one algorithm, like Metropolis Hastings one, we then not necessarily have them approximate posterior from scratch all the time. We then move on to tools that are more commonly used by practitioners, such as rstan. So it's basically this R wrapper for the stan language. And you might realize that if you've never used stan before, the code on the left does not necessarily look like an R code. It's because it's stan. So there's also a learning curve of these stan. And I know that many others also choose to teach Bayesian courses with JAX, for instance. So this also adds some additional learning curve for students. But there are also other resources that we also rely on, like rstanarm. So if you look at this code, for instance, if you've never done Bayesian analysis, but if you've done regression analysis in R, this code will not look that different than a regular regression model, linear model in R. So we rely on all these tools, actually approximating the posterior from scratch, rstan, which actually requires some stan learning, and also rstanarm. So they all each have their own piece. For instance, we use rstan so that students actually understand how each parameter plays a role and how to set priors for each parameter. But once they understand that, once we move on to more posterior analysis topics like posterior prediction or hypothesis testing, we just rely on built-in functions like rstanarm to just get to the posterior fast, and then use the posterior to learn more, to make more conclusions from the data analysis. So all of these play a role in the course. And I'll mention the pedagogical approach a little bit. So I mentioned checking intuition. So this is, I think, any probability course and Bayesian course, it should be part of that. Students do have their preconceptions about probability or Bayesian approaches. So even their own beliefs, checking their own beliefs about Bayesian statistics, like having a prior is very important, what their intuition, how they feel about it. So one way we do this, for instance, like checking their intuition is the quizzes, but also when we first start the course, we have, that is also in Unit 1, I also do that activity in my first day of class. We have this quiz that basically shows them whether they are Bayesian or more frequentist inclined at the beginning of the class. It's not a competition, but it really helps to see how students are feeling about hypothesis testing, probability, and so on. We do have a lot of those quizzes and coding. Our idea behind them is to enforce active learning. Students are actually doing those themselves. So it's not just they're coming to the lecture and just listening, but they're actually, even if they're just doing it in their head, not necessarily responding to questions online, they're, I think, extremely important part of learning, because they once they do the analysis, they see if they're what they thought was correct or incorrect. And it's a little bit of my privilege to be in a computing school, but I do really enjoy teaching, and students really enjoy learning this way too. We do teach computing and math together at the same time. So they do actually know computing technically when they come in, but it really helps them to use all those computing skills. Like in their statistical computing course, they learned about iterations, writing functions, and so on. But then they get to actually put it to use for a real algorithm, for instance. So these are, I think Bayesian course is a great opportunity for them to get them to use their computing and math knowledge together. And the general approach for computing we have is, if students are able to compute it from scratch for a single case, then we move on to relying built-in functions, because we are not necessarily testing whether they can keep writing things from scratch, but if they're able to understand what is going on behind our functions, what's the black box telling us, that's our goal mainly. And writing this book and also teaching this course, we've focused with my co-authors a lot on making it accessible and inclusive. And we've learned a lot of things in the process. It's really beyond the scope of this talk, but for anyone interested, I linked it to a preprint about this approach we took to accessibility and inclusivity in this book. And lastly, I want to share a few things that might be useful. One of them is we have a resources webpage. A few of my colleagues, we've put this together. So if you're interested in teaching Bayesian course, or if you already teach one, there are some published papers on undergraduate Bayesian education. So this is specifically for undergraduate Bayesian. And there are textbooks that you may want to look at. So these are some resources that you may find helpful. Last but not least, we also have an undergraduate Bayesian education network. If you're interested in joining, feel free to email me. I'm happy to add you to that network. It's a good place to exchange ideas about our own courses. That's all I have for today, basically.
Mina, thank you so much for that. It's been really interesting to see how you've managed to teach Bayesian statistics in a very inventive way. So I'm going to open the floor for questions now. So please do pop your hand up if you would like to ask me any questions, or pop them in the chat, and I will happily read those out. While I just wait for questions, I have so many to ask you. Oh no, actually somebody has put their hand up. Mark, do you want to go first?
Yeah, sorry for hogging all the questions.
That's all right.
Just a question about the order in which you're teaching the simulations. Is it correct that you teach them how they write the Metropolis Hastings algorithm themselves, and then you go on to teaching them STAN, and then you go on to using STAN, rstanarm?
Actually, so in the book, we actually first, no, that's the order, sorry, okay. For a second, because I teach slightly different than the book, but this is the order I also accompany in the book. I think in the book, we first do rstan, we show the rstan, and then we go into like, why does it work the way it does, sort of later. Yeah. But in my course, I do rstan, from scratch, rstan, then rstanarm.
Great, cool. And sorry, it's a quick one. Do you have any thoughts on BRMS versus rstanarm?
So we get this asked a lot. Actually, for anyone who doesn't know, there's a great Learning Bayesian podcast. This one in one of the resources. And I was asked on that podcast too. And I don't have any strong opinions about that, but I know that there's a person on Twitter, at least, who tried to change our book code to BRMS. So it might already be available somewhere on the internet. But we just chose rstanarm at the time because we were more familiar with it and there was more resources on it, at least the ones we accessed. But as far, I've never used BRMS for teaching or learning.
It was probably was it Solomon Kurtz who changed that? Because he often translates things into BRMS, a lot of books.
Yeah, sounds familiar. Yeah, I'm not sure about the name though.
Okay, thanks.
Mm-hmm.
Alan.
Yeah, thanks, Elena. Sorry, it's taking me a while for the computer to respond to me clicking on mute and the video. Mina, I was thoroughly fascinated by the talk there. are you teaching students that are specialist mathematicians, statisticians, that sort of thing, data scientists? Or have you got any sort of experience and therefore any sort of suggestions for how to go about teaching Bayesian statistics or supporting Bayesian statistics to non-specialists? Because I think you said at the start that the future is Bayesian, and I don't disagree with you, because I think you know, as more and more students are having to learn and take on machine learning techniques, etc., a lot of which is kind of underpinned by Bayesian methodology. So I just wondered if you've got any experience of non-specialist teaching.
Mm-hmm. So one of the studies I'm involved in now, so I recently got working and thinking about like how to make Bayesian be more accessible at K-12 level. Especially, I started working with Joshua Rosenberg. He focused on science education and like how it can impact scientific thinking in the classroom. So with him and another collaborator in Turkey, Sibel Kazak, we tried to build a Shiny app to help teach Bayesian thinking at the very basic level to math and science teachers. That was our goal, so that they can actually take it to their classroom. So that's one. And basically, whatever I've shown about like plotting beta binomial, all those things, actually, we don't necessarily have to say it's a beta. We can, like, what the approach we took is still a proportion. They can talk about a proportion. They can make like they can actually state their beliefs about a proportion, prior beliefs. So we use that. Like for binomial, for instance, we couldn't use terms like number of successes, number of trials. So we tried to eliminate all those terminology and tried to develop a lesson plan for them. And it went well. It was our first try, and we're hoping to publish about that as well. And also another one like Joshua and other colleagues, and actually that's published already as a preprint. You might find it on my website. For science classes, basically that one doesn't necessarily have any calculations at all. It just says like, what was your belief? How strong were you in your belief before you started this analysis? This is for a science classroom, so they have a hypothesis for some scientific phenomena. And then they observe some data. What did the data say? And then it calculates some posterior for them. Like this is what's your. So I think without any Greek letters, without terminology, we can still do a lot of Bayesian thinking. And also for anyone interested, who I will drop a name in the chat, Sibel is a good person to read for kids. She works with kids on Bayesian thinking, like subjective probability in kids. So she's phenomenal in that. So I think we can teach Bayesian early on too.
Brilliant, thank you. Yes, that's really useful. Thank you.
So Mark, do you want to ask a question?
Once I've unmuted, yes, I do. It's a bit of a sideways comment, but more than a question. As a sufferer of statistical teaching, I was a practicing doctor for 40 odd years in the NHS. I've now retired. The great revelation to me was when I was introduced by a certain Professor Spiegelhalter to Bayesian statistics, because suddenly it fitted real life. All the previous learning I had endured under frequentist methods was such a load of complete, yeah, you can fill in the words, that I suddenly saw that statistics might actually be useful to medicine in the real world. And my question really is, why do we still bother teaching people like medical students, physiotherapists, nurses, etc., frequentist type statistics? Because it's a load of rubbish. We all know it is. And it's based on a complete set of fallacies. And yet I'm a heretic for saying that. So why do we insist on teaching rubbish to students who then get afraid?
I actually have a comment for that. So, I don't know if you're familiar with American Statistical Association's statement on p-values. So it actually begins with a quote from George Cobb, who is who was an amazing statistics educator. And he says, why do we teach p-values a threshold of 0.05? It's because scientists use it. Why do scientists use it? It's because we teach it. So it's like a loophole that we are stuck in, in the stats education community and the scientific practice. And hopefully, like with more Bayesian efforts, that will change. And to be honest, my favorite part of teaching this course is the chapter on hypothesis testing. That's the chapter where my students fully understand p-value. It's a Bayesian course, but they understand p-value. And they usually give reactions like, wait, were we always lied to all this time? Like what they thought of p-value is not necessarily like what they think it is. So a Bayesian teaching actually helps us also understand, in my opinion, frequentist statistics as well.
Irini.
Really, it's just a comment to Mark's question, and Mina, I hope you don't mind me adding my thought too, because I get asked the same question from the short courses. I ask it myself often because we run an introduction to Bayesian course exactly with the aim to get people to understand what Bayesian is, how is it different to frequentist, and the question at the end is, why don't we just do that then? You know, why do we bother, as Mark said? And my answer to that is mainly very practical. I say to our participants and our students, I say, well, because until very recently, you weren't able to do it on mainstream packages. SPSS, which is the main package, software the institutions, academic institutions support, it wasn't possible. It's very amazing to see that version 28 at the moment has a Bayesian analysis section, which is fascinating. I think for what, as many of us I think are agreeing here, that it's the future. But I think on Mark's point, medical students, they come there, they've got 5 years, at least in the UK, of medicine to learn. And then if you told them, oh, you also have to learn R or Stata or Python or SAS, because we want you to do Bayesian, I think we would have lost them there. But I think it will change. At least that's my take of it. Now that we have the tools more readily available, I think the change will be bigger and more prominent in the years to come.
Thank you for that, Irini. I've just spotted a comment from Simon in the chat. He says, as a statistician, frequentist stats is obviously not rubbish. However, it is taught and used very badly. And I think there's a lot to be said for that. So Mina, perhaps just a question from me now, just to tie in with what Irini just said. So in your course, do you spend time discussing with students the differences between Bayesian and a frequentist outlook?
Yeah, absolutely. We even like the first day activity we start with is that also like how Bayesians and frequentists have different approaches to analysis. Even like remember the Sogi restaurant figure I have shown, like, so that's what we start with, like the prior, more information, and frequentists, we just show data, that's it. So they start from day one, making comparisons. And I agree with Simon, like our aim, like I never actually force my students to be Bayesian, like frequentist statistics is also very useful in its own way. So we try to balance that throughout the course too. Like, it's like our job is to make them understand both of the worlds, like rather than take sides.
Very interesting. Well, it's been fantastic to see how much discussion that's generated. Perhaps there is a call for having a dedicated session to thinking about how and why we should be teaching Bayesian statistics some point in the future. I'm very aware, though, that we are now past 5 o'clock, and the very kind people at TALMO, it's beyond the time that we said that we would finish. So let me just finish by saying thank you ever so much to all our speakers. It's been fantastic having you. It's been really interesting hearing what you've had to say. And thank you also to the TALMO 3 who are continuing to work so hard in putting on these events. So thank you very much to you 3 as well.